Today's topic is about mixing. Whenever we hear a term that is anything about mixing or agitation, something like that, the first thing that comes to mind is okay, there are uh, two or more than two different materials, and now we have to force them so that they get mixed with each other using some external means, right? So that is basically a rough definition of what you can give about mixing. So it is nothing but a physical process where you try to reduce the non-uniformities which are present in the phase that you're dealing, and then you eliminate the gradients, be it with respect to concentration, the temperature, or any other characteristic property of the material that you are using. Okay. So in mixing, basically you have two or more phases. And when I say phases, it just does not mean that solid, liquid, and gas, but it means any substance which is uniform throughout in its physical and chemical composition. So that we define as one phase here. Okay, so when you have at least two separate phases, and when you try to bring them together so that uh, whatever the differences are, differences in the concentration or the temperature or any of these properties, if this exists within the vessel or the container in which they are placed. So you want to get them, you want to have a homogeneous mixture where these properties are well distributed. And to carry out that, you do a process, a physical process, which is called as mixing. Okay. So you have a homogeneous mixture and heterogeneous mixture, right? So we know when we say homogeneous mixture, so in that case you can just say any two components which are miscible with each other. Those would constitute a homogeneous mixture, and whenever there are two or more than two components which are present but are immiscible with each other, those are termed as the heterogeneous mixture, right? So in this concept of mixing, we are going to talk about both these types of mixture. So homogeneous mixture as well as the heterogeneous mixtures. Okay. So the type of mixture that we will be dealing here will be like liquid-liquid mixture, gas and liquid mixture, liquid with solid, and solid with solid. So the aims or the objectives of mixing are basically to promote a reaction, right? Because when the two reactants, when they are in when they come in sufficient contact with each other and they get an appropriate amount of time to get exposed to each other, then only your reaction will proceed further, right? And for that, you need to have a homogeneous distribution of the material throughout the reaction, or else you will have the localized spots. Like in one place in the vessel, you will have your reaction taking place, but at the other, because there is no contact between the two reactants. So in that case, you will not have a reaction taking place at one point at one point in the vessel. So to have a homogeneous way of doing reaction within the vessel, and to have a more efficient running of the process, it is needed that you have sufficient mixing taking place. Then at some places you would need, you have two different components, but then you want a kind of mixture which is a part of your final product. So to produce simple physical mixtures, as products, then The third one will be to carry out any physical change. Right. And then the fourth one will be to obtain sufficient dispersion in a mixture including solids. So let's say in some case you need to have solid suspension. I mean, those would not be the solids which would get mixed with the fluid that you're dealing, but still you would want to have a regular or a homogeneous suspension of the solid in that material. So in such case, you need to have the suspension uniformly distributed, or else again, one phase of uh, one phase of your material will be comprising of solids and the other would be just plain liquid. So in order to have a homogeneous distribution of the solids in such suspension, you need to have mixing taking place on a regular basis, right? So these are some of the practical objectives of the mixing process. And then you have some equipments which are used to carry out this mixing. And basically you have the equipments that you need to use for it is nothing but a, a kind of a vessel where you will have this mixture of materials present, and then you have another part of it which we call it as impeller. Okay, so impeller is nothing but impeller. So this is your vessel in which you will have your mixture of materials. Let's say you have your fluid filled in up until here, and then this is your impeller, and this is your shaft which puts your impeller into the fluid mixture, and then through this impeller you try to mix in the materials which are present. And then depending on the type of there are different types of impellers which are used in the industry, and depending on the type of impeller, you have to make sure that the configuration of the vessel itself is propagating the function of your impeller. It should not be like the aim is to have a homogeneous mixture, but then at the end, because of the configuration of vessel what you have, there are possibilities that it might just hinder or it might just negate the effect of propeller, so that impeller, so that in case again there would be a chance that at one point or at one particular section of the vessel you have a very well homogeneous mixture of the materials, but whereas in the other section you still have a very you can say a very distinct kind of a composition of that material. So let's say in this case, if there might be a possibility in case of a non-ideal mixing in the vessel, that you will have all of your you have component A and component B. So you have a very uniform composition of A and B here. But in this case, it is very random or very lean concentration of the component A in this. So although you have uniform composition in these two sections, but still it's not homogeneous throughout the vessel, right? And that is what we need to have. Otherwise, if you just wanted to have some random distribution, or even two separate different types of distribution, then you would opt for a different configuration of the vessel. But for any general application of mixing, you would want the composition to be uniform throughout. So along with the type of impeller, you also need to look into what should be the configuration of the vessel. And that is something which we are going to talk about in the later part of our discussion. Okay, so this impeller is the most commonly used equipment for the mixing operation, which involve liquid-liquid mixtures, and to some extent where you have a very small amount of solid present in the liquid. Even in those cases, you can use these impellers. But then when you have a mixture of solids or very viscous fluids, in that case you deal with the different types of mixing equipment. Okay, so those also we will be discussing later. But for now, let's look at mixing liquids with liquids. Okay, so as I had shown in the previous diagram, the general form of equipment which is used is basically a vessel with an impeller or an agitator, and because of this, you have your mixing taking place in it. So then, in such cases where you have a vertical vessel with shaft, rotating shaft here, and then you have your impeller, something like this. And then sometimes you also have baffles here to create a kind of disturbance. Okay, so in such equipments, the usual configuration what you want to have is that the height of the vessel what you are using, it would be somewhere in the range of 1.5 to 2 times of the diameter, right? So this is the diameter, and the diameter of the impeller what we are using. So the diameter of the impeller is approximately 1/3 of the diameter of your vessel. Okay, and this agitator or this impeller what we are using is usually driven by an electric motor, and this vessel here is, so in case it depends, in case if you are trying to do a batch or a continuous reaction, so this your vessel would be having, if it is a continuous one, it will have a provision for the inlet and an outlet, and then a heating coil or a jacket in case if the stirring or the mixing needs to be done at certain elevated temperature. So we know that for in some cases, in most of the cases, your when the two materials that are in contact with each other and they have certain tendency of getting mixed with each other. So in those cases, as you increase the temperature, its solubility would increase or the miscibility would increase. So in those cases where you have like, you need to have a very concentrated solution. So in those cases, you will have to provide certain heating, and that could be provided when you have your some heating jacket around this vessel. Right. So this is just how the basic configuration of any mixing or an agitated vessel would look like. And then coming to the size, so obviously depending on the scale of your operation or the type of your application, uh, it would the size of the vessel that you are going to use would be defined because based on the type of product as well as the scale on which you are operating. So considering the size of the vessel, there are certain ways in which this impeller can be used, their alignment or their configuration within the vessel, as well as the type of impeller can be that can be used, depends on those factors. So basically, when you are told that you have number of options based on your vessel size and vessel construction, your impeller could be divided into two types. One is your axial flow impellers, and the second one is your radial flow impeller. Okay, so what happens in axial flow impellers is that these axial impellers, okay, so first let's talk about okay, so the basic difference between axial flow and radial flow impeller is that the axial flow impellers, they generate the flow currents or the flow patterns which would go parallel to the axis of the shaft. Okay, so in axial flow impellers, the flow currents are parallel to the axis of shaft, and hence the name axial flow. Okay, and in radial flow, they generate flow currents in the tangential or in the radial directions. Okay, so when you have motion of liquid, so let's say so in this case, let's say if you have your motion of liquid and your shaft is moving in this direction, so your radial flow will be something like this. Okay, so because of the circular motion which is being generated here, so this along with the tangential flow uh, to the circular motion induced by these impellers, these kind of flow currents would be generated by your radial flow impellers. Okay, and further, depending on the configuration of your the blades or the impeller dimensions, you have further more varieties based on which it can be classified, which includes propellers. Second is paddles, and the third one is turbine. So these three are based on nothing but the configuration or the design of your impeller. And the first two, which is your axial flow and radial flow, they are classified based on the flow currents or the direction of flow currents which are generated by them. Okay, so based on the two different classification methods that we discussed, so among them, your propeller and pitched blade turbines, they are axial flow impellers, whereas your paddles flat blade and curved blade, these are your radial flow impellers. Okay, so just I've just mentioned the names here. I'll show you in general how they actually look like. But Yeah, so first let's see how the propeller is. Okay, so the most common one and the one which you must have seen very often is the three blade propeller. Which is something like this. Okay, so you have your three blade propeller, and this is the point where it is connected to the shaft. And then most of the time it is something which is which we must have seen in any of our lab experiments where we have a batch reactor and then you have to provide a very high speed stirring. So in those cases, these propellers are used. Okay. So these propellers, or this is like, as I mentioned, this is the three blade propeller. And these are typically the high speed ones. So in case where you have a very large vessel, there it is possible to use such high speed propellers for mixing, and they would be sufficient enough to so as to not cause any kind of uh, a localized spots where you have only certain concentrations at one point and a different concentration at the other one. And then as I mentioned, if you have a very large size, then there are different ways in which you can use this propeller. One is the vertical alignment, and the another one is the sideways alignment of this, where you can have your propeller aligned through one of the sides of the vessel that you're using. Okay. So this one is what we call as the centrally mounted propeller. This one is your sidewall mounted. And then there is also possibility that instead of having it perpendicular to the surface of the liquid, you can also align it in a different direction, something like this. Okay. So the reason why you have a different alignments or the different mounting of these propellers is because at certain points when you are operating at a very high speed, there is a chance that it might lead to formation of vortex, right? And because of the formation of vortex, it is possible that it would create a very huge pressure difference, and it might lead to a case where it might suck in the air which is present just above the surface of the liquid or any of the component which is present there. Okay. So again, that is one component which we will talk about when as we move along. But the reason why we have the different mounting or different alignments of the propeller or any of the impellers that are used is because we do not want to have the localized spots or the formation of a vortex which would create a disruptive uh, fluid profile, and because of which you will not have adequate mixing taking place. Okay. So then after propellers, you have your turbines. So the turbine impellers, they are also of different varieties. So one of them would be like, let's say, straight blade, where this would be something like so this is something what it would look like from the bottom view, and then from the side view, this is the point where the shaft is connected, and then In the side view, it would look like something like this. Okay, and then you have the another one. However, this is not much very commonly used, but still the most simplest one is the open street blade. This is the next one is your flat disc blade, which is something like this. So you have a disc here, and on this disc you have certain blades attached. Like this. And then again, from the side view, there won't be much difference, but something like this. So this is how your flat disc blade would look like. Okay. And sorry, this one is in this, the connector between your shaft and your blade is not this thin. Here it would be somewhere of the same size as that of your blade. Just draw it again. Something like this. But here, when you go to flat disc blade, the difference in the size or the difference in the width of your connector and your blade is going to be much more prominent. So this one is your flat disc. Then after this, we have another which is way more commonly used than the flat disc blade, which is your vertical curved blade turbine. So that would be something like this. So you have this one looking something this way, your vertical curved blade, right? And then after this, you have the other one, which is more of an axial flow turbine, which is your pitched plate turbine. Okay, so in pitched plate, you have your rectangular plates attached at certain angles to each other, because of which you do not have any of the radial flow taking place when the impeller is used. So I'm just trying to give you an idea of how the different angles would look like. So let's say this is something, one of the blade is like this, the other one so if this blade is in this direction, then you have another one which is again at a certain angle to the shaft. And then this one too, maybe at a certain angle to the shaft. Maybe not that quite a good representation. Let me just see, because this is again based on the type of flow which is desired, or the mixing pattern which is desired. It is an important type of turbine. Okay. Mm, just a second, I'm trying to share the screen. Yeah, something like this. Okay, so this is how the alignment of the blades are with respect to each other. So they are inclined at a certain angle with the shaft, obviously not making a perfectly 90-degree uh, angle with the rotating shaft. And then because of this characteristic alignment of these blades, it is very much difficult to have more of a radial flow or the tangential flow along these blades. So in that case, you have more of the axial flow is the dominating one in the case of the pitch blade turbine. Okay. So that is how your pitch blade turbine looks like, and compared to what it is, what we saw for the straight open straight blade and the vertical curved blade, it obviously has a slightly different configuration. Okay, so these are the types of turbine. Let's now look at the specifications of what are the ones which are generally used. Okay, so the ones which are most commonly used among the turbines, as I mentioned, they include the vertical curved blade and the open straight blade. Okay, and these are the ones which have more effect towards generating your radial flow currents than your axial flow. Yeah. So we were discussing about turbines, and they the commonly used turbines are
Hello.
effective
Hello.
to develop radial currents. But then, if the turbines which are being used, if they are generating more and more radial current, and as you increase the speed of the turbine, as I mentioned, it would lead to a form. It will lead to a situation where you will have your fluid profile something like this. Okay, so this would be the beginning at where your vortex formation would take place. And then as you increase the speed more, with the thinking that, okay, as I increase the speed and if the fluid which is used is slightly more viscous, so let me just increase the speed, but at certain point, if you increase the speed even beyond this,
Hello, sir.
then your vortex formation would go until the point where you have your impeller.
Hello, sir.
Okay. So these two phenomena are something which should be avoided at any cost, because then that defeats your entire purpose of having an impeller and causing the mixing of the materials. Okay. So to avoid this, any oh, okay, sorry, I think I forgot to share my screen. So let me just start again. Yeah. So what I was mentioning was the turbines which are most commonly used, as I mentioned, the straight blade turbine or the vertical curved turbine or any curved blade turbine. So in those cases, what you have is your radial flow being the dominant one. And in such cases where you have the more dominant radial flow compared to the axial flow, it is highly probable that the vortex formation would start taking place. And when I say vortex formation, it means that you, I mean, from the visual point of view, your the fluid pattern would look something like this, that it would start forming a kind of V-shaped profile. So initially it is something like this, somewhere at the moderate speed, but then as you keep on increasing the speed, let's say if you believe that the mixture that you are going to form or the liquid which is being used is slightly more viscous, so in that case, if you increase the speed, then your vortex formation would look something like this, where it would be a proper V shape. So then because of this, there would be a considerable pressure drop. And then if there are any other components, let's say uh, even there is a possibility that your the feed mixture or the liquid mixture it might be susceptible to reactivity or some kind of interaction if it comes in contact with the air along which is present on the surface along the surface of the fluid. Then it might get just drawn into the fluid mixture, and then it would lead to addition of more air bubbles within the liquid, which is again something which you would not want compared to the fluid which was initially present uh, in your mixing vessel. So in such cases, you have another equipment or another provision called as baffles. So the baffles are the ones which are used so that your the currents generated because of the radial flow and the tangential flow from these radial flow impellers, those would get cut off to a certain extent, and more so the tangential flow. Because of the baffles, uh, the fluid moving along the radial direction after hitting towards or after moving towards the wall of the vessel, it might form a kind of pattern something like this. Right. So let me show for an unbaffled tank. And a baffled tank. Okay. So for an unbaffled tank, so this is how your this motor is running, and then for an unbaffled tank, you will have your radial flow. This is your tangential flow, and then this is your axial flow. Right. So when you have an unbaffled tank, there what you do is you provide sufficient space for the fluid in motion so that it goes to a point where it makes tangent with respect to the circular motion, and then again goes back towards the center of the circular motion which is happening inside the vessel. And as you increase the speed, what will happen is only these motions will start becoming more dominant compared to this axial flow here near to the shaft, and because of that you will start having more and more of vortex formation taking place as you move along the time. Whereas in baffled tank, okay, before this, is there any other application where you have heard of the term baffles? Shivam?
Hello. Hello. Hello.
Still not able to connect to the audio. Okay, so let me just, yeah, right. So in heat exchangers, right? And in heat exchangers, what was the purpose of having baffles?
To have more.
Right, to create turbulence, right? So similarly here, the purpose of having baffles is more or less the same. So what you do is compared to the generic flow, what is generated during the movement of impellers, you try to disrupt that flow. So in that case, you do not, so you will have your baffle somewhere towards the side of your vessels here. And then again, the same motion, you will have your impeller moving along. So what will happen is, because of the presence of baffles, you try to disrupt the flow, which is usually caused by the movement of your impellers, and then you do not allow for the tangential flow of your fluid to take place. So before it would form or before it completes the radial flow, you will have your baffle standing along in that path and then disrupt that flow. And because of this, the flow of the fluid in the tangential direction would not take place effectively. And then because of that, you would not have a tendency for this vortex to get formed. Okay, so you disrupt this kind of a flow, and then after one point, it would just this flow would get collapsed as soon as it comes in contact with the baffle, and then you have a mixing taking place here. And even in such case where you increase the speed, it's only the rate of collision of the fluid with the baffle would increase, and which would just create more turbulence and then hence more mixing. Okay, so that's why using baffles in such cases is advantageous, or in certain applications where it is pretty much sure that after a certain point, it would lead to vortex formation. So then making use of baffles makes much more sense with respect to the efficiency of power which is being consumed to obtain the same degree of mixing, as well as to obtain a more homogenized mixture of the fluids within the vessel. Okay. So that is one very important aspect, especially when you are using the turbine type impeller. In those cases, it is necessary that we have baffles present within the vessels. Okay, so after this, we have so as I mentioned, there would be different types of flow pattern depending on. I mean, you will have different types of flow pattern present in the vessel, and these flow patterns, they depend firstly on type of impeller, as we just discussed. Then second, characteristics of the fluid. So if you try to have or if you increase the power of your impeller for the same degree of power, let's say for a very less viscous fluid, the velocity might be different, and then for highly viscous fluid, the velocity might be different, right? So then, but you cannot assume that given the same amount of power which is being provided to the impeller, uh, the flow pattern generated in both the cases would be same, because of the characteristic of the fluid, the speed of the impeller would not be the same, because it has to overcome the resistance offered by the viscous force of the liquid, depending on its characteristic, right? So another is the characteristics of the fluid. Then third one is size and proportions of the vessel, baffles, and agitator. And then the next one is the operating conditions of the impeller. Okay. So again, size and proportion. So if you have a very large sized tank and you use an extremely small size of your agitator, again that would create a different flow pattern and the different mixing behavior which would be obtained, and hence your final composition of the fluid, that would be different. So the proportion of each of the three components, which is your baffles, the agitator, and the vessel, would be very important in determining how efficient your mixing is taking place. And obviously, the efficiency would be dependent on the type of flow pattern which is generated because of these components. And the fourth part is, or the fourth factor is the operating condition of the impeller, which is basically the size with which it is being rotated. Okay, so these four characteristics, or these four parameters, define the flow pattern and hence your efficiency of mixing. Right. And this another aspect, or another way in which you can avoid formation of vortex is something which we had just discussed in brief, and it was about off-center mounting of the impeller. Okay, So this off center is nothing but this is something you're centrally mounted. The off center is something where it is not exactly at the center of your geometry of the vessel, but somewhere on the sides, something like this, or at a certain angle, something like this, or on the sides of it. Okay, so in small vessels, these kind of different alignments or mounting of the impeller might be of much better use as compared to the large vessel. And so like the vertical alignment in smaller vessels, vertically mounted impellers are preferred, whereas for larger vessels, vertical as well as side entering propeller are feasible. Okay, so with side entering, I mean to say this, and vertically are like these two. So off center or the centrally mounted, as well as the off center one, they can be used in smaller as well as larger vessel. Whereas if you want to use the side mounted impeller, those are efficient or those are much more practical only when you have a large vessel under consideration. Okay, and in case if you are using larger vessels for mixing, and let's say the design of your vessel compels you to use only the vertically mounted or vertically aligned agitator, in that case, to avoid formation of vortex, you can make use of the baffles as we discussed before. Okay. After this, you have the third type of impeller, which is paddles. So, and in paddle agitators, what you usually have are the vertical agitators with 2 to 4 blades, and these agitators are something which extend close to the wall, and because of the large nature of these paddles, the motion or the current generated is mostly the laminar regime flow. Okay, so this is something, the one which you must have seen a lot often is the anchor type paddle, which looks like this. Okay, so this is a kind of your anchor type paddle. Then another one which is your flat paddle. You have shaft like this. And you have blades aligned in this pattern. So this is your flat paddle. So these two are the ones which are more commonly used. And then you have another two types of paddle which are known as gate paddle and combined paddle. So in both these types, what you have is then here. Okay, so something like this. So here it's not only these blades which move along, but it's also the periphery of it. And because of the movement of the blade along with the peripheral of these paddles, they sweep the entire area to which they are exposed. Okay, so in case where let's say you have a high concentration of solids present in the liquid, so in such cases you make use of this gate and combined type of paddle uh, where these extended surface or the periphery and these blades almost reach towards the wall of the vessel, and then there are possibilities, right? So like when you have a very high concentration of solids present, those might just get stick to the walls of the vessel, and because of that, if you do not scrape it out, then you would lose most of it, most of the solids which is stuck to the wall. And obviously, if even if you try to recover it, you will have to spend a considerable amount of time first, because then you would have to withdraw or draw out the liquid from the vessel, and then do the scraping operation later when the entire liquid is being has been emptied out of it. So then, to avoid such a situation, you make use of these type of paddle in the cases where the mixture that you are dealing with is consists of more amount of solid materials. Okay, and in case if you do not have such provision where you have you where you can scrape off, or where you can remove the content which is stuck on the walls, in such cases there are high probability that you will have localized hotspots taking place, right? So if you are trying to mix it under a very uh, high not very high temperature, but if you're trying to mix it at a normal temperature, then it's fine. But if you want to improve the solubility of those solids, in such cases you will be operating at high temperature, and if these solids get stuck on the wall, these would find and we know from certain basic application from the heat transfer that you will have an additional film resistance which will be offered because of the presence of solid, and that heat that you are providing to the vessel will not ultimately reach to the liquid mixture or the feed mixture that you are using in the vessel, right? So when because of the presence of these type of paddles, you prevent the deposits on the heating surface, and in case even if you are doing the reaction, so in that case reactions vessel, and they improve the heat transfer in such cases as compared to any other type of impeller used in these kind of applications. But one drawback for them is, compared to the turbines and the propellers, I mean, all the paddles, they are a relatively poor mixing equipment. Okay, because the blades or the impellers which we are using here, they have such a large dimension that they uh, will not be sufficient enough to give a much better contact area between the two different phases that we are using here. Okay, so it's more like on a superficial level. So like they provide kind of a superficial mixing, whereas the turbines and the propellers, they provide more of an intimate mixing. Okay, but then again, depending on what type of application you are using, you have to choose the appropriate type of impeller. Okay. Okay, so then after this, we will move to another topic, which is about the power consumptions of the impellers. Right. So what we'll do is we'll take a 10-minute break now, and then after that we will meet ahead and then finish up the topic of mixing, and slightly begin about the next subject, which is chemical technology. Okay, so we'll meet in another 10 minutes to discuss about the only part of mixing where there is a possibility of any numerical being asked about it. Okay, so see you back in 10 minutes. Okay, so let's begin with the next topic, which is power consumption of impellers.
Hello, sir. Hello. Hello, sir. Hello, sir.
Okay, so as we had seen, for the agitated vessels, the impellers are usually driven by electrical power. So there is an empirical correlation for the power, and which is dependent on the other variables of the system, which gives a relatively accurate prediction of the power requirement for a given impeller. And this correlation is a function of geometric details or the geometric configuration of the impeller, the vessel, the characteristic of the fluid, which includes the viscosity and the density, and the rotation speed of the impeller. Okay. So the relation goes something like NP is a function of your NRE and NFR. Okay, so NP is your power number, NRE is your impeller Reynolds number, and NFR is your Faraday number. Okay. So we more or less know what is the significance of the Reynolds number, right? So in case of impellers, when your NRE is greater than 10,000, then the flow is said to be turbulent. However, when your NRE is less than 10, then the flow is laminar. And when it is between 10 and 10,000, it is said to be somewhere in the transition region, where the flow is turbulent at the impeller, whereas it is laminar in some parts of the vessel. Okay. So this was about the Reynolds number. However, the Faraday number, which is indicated by NFR, it indicates the influence of gravitational force and its effect on the power consumption in case where there is a probability of formation of vortex. Okay. And as we had discussed before, when the speed of the impeller is increased, and especially if we are using unbaffled vessels, so the centrifugal force acting in the liquid results in the formation of the vortex, right? And this vortex can be avoided by the use of baffles. So in case of agitated vessels, when your NRE is less than 300, there is a high probability that your vortex may not be observed in case of unbaffled vessels. Okay. I mean, in case of baffled vessels, it's an altogether different situation. But even for unbaffled vessels, if your impeller Reynolds number is less than 300, then there is a high probability that your vortex formation will not be. I mean, there won't be any vortex formation in the agitated vessel. Okay. So, in such a case, your Faraday number would anyways be insignificant, right? Because that is the influence of the gravitational effect and how it affects the power consumption only when there is a vortex formation taking place. So when your NRE is less than 300, in such case, your power number will only be a function of your Reynolds number, right? So then at lower Reynolds number, your power number can be written as NP is equal to C0 by NRE, where C0 is a constant for a given impeller and geometric configuration of the vessel and its component. Like it depends on uh, the size of the vessel as well as the type of impeller which you're using. So based on that, you have a constant given as C0, and NRE is anyways your impeller Reynolds number. So then what you have next is NP into NRE is equal to C0, and your power number is defined as P divided by N cube dF to the power 5 into rho. Okay, where P is your power, N is your rotational speed given in terms of revolution per second. dA is diameter of impeller, and rho is density of fluid. Right, so this is your power number. Then your impeller Reynolds number, which is your NRE, is given as N dA square rho by mu, where the other terms are the same as I mentioned earlier, and mu is your viscosity of fluid. Okay. So from this definitions of power number and impeller Reynolds number, and considering the equation which is here, let's say equation 1. So once you put equation for the formula for power number and Reynolds number, what you obtain is P is equal to C0 into mu to dA cube into n square, right? So considering that, okay, C0 is anyways a constant depending on the geometric configurations of the vessel and the type of, or for that particular impeller, then based on these definitive properties, depending on the characteristic of fluid, the dimensions or the configuration, or sorry, the size of your impeller and the speed with which your impeller is supposed to be moving, based on that, you can tell how much is the power requirement, right? So this is applicable in case of low Reynolds number, or when your Frodde number is of insignificance, that is when your Reynolds number is less than 300. For higher Reynolds number, the Frodde number would be of much more significance now. So in that case, your power number remains constant. That is your NP. And let's say give it a C dash. And then using the definition of power number, impeller Reynolds number, and Frodde number. So your Frodde number is given as n square dA by rho. So then what you have is an equation where you have power is equal to C dash into rho into dA to the power 5 into n cube. Okay, so considering the situation, or considering the operation taking place in the vessel, and finding out what is the impeller Reynolds number, you have to make use of the appropriate equation to find out the power consumption. So this is for higher NRE. Right. So if we just compare these two equations, let's call this as equation B and this as equation A. So if you increase the speed of your impeller 2 times for when it is operating under a very low Reynolds number regime, so in that case, if you increase the speed 2 times, your power consumption will rise, or it will increase by 4 times, right? If you consider equation A. So if your n dash, or your new speed becomes 2n, so your power requirement will become 4 times more. Whereas if you are already operating at a higher Reynolds number regime, and then in that case, if you improve the speed 2 times of the initial one, in that case, your power requirement would go 8-fold more. Right. So it is very important to first find out under which regime is your fluid present in your agitated vessel, and then based on that, use the appropriate equation to find out the power consumption. Okay. So we'll do one question based on this. Shivam, is your audio issue resolved now, or it's still the same?
Hello, sir. Hello. Hello. Hello, 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 hello. Still not working, so.
Okay. So I'll dictate the question. Maybe you can note it down then. A six-blade turbine agitator. A six-blade turbine agitator of diameter 60 centimeter. Of diameter 60 centimeter is centrally mounted. Is centrally mounted in a tank with diameter 180 centimeter. In a tank with diameter 180 centimeter and at a height of 60 centimeter from the bottom. And at a height of 60 centimeter from the bottom. The tank is filled with a solution. The tank is filled with a solution of viscosity 10 centipoise and density of 1.45 and density of 1.45 gram per ml. The speed of agitation is 90 rpm. Then calculate the power required. So first, tell me what is the impeller Reynolds number. Yes, did you find the value of impeller Reynolds number? 4698000. Okay, so based on the impeller's Reynolds number, we will be using the condition where your power number is constant, right? Because now it's in the turbulent region. So in that case, you have to make use of the equation where your power could be found out by using P is equal to C dash into rho into dA to the power 5 into n cube. And in this case, your power number or your constant C dash for this configuration is given as 1.05. Pay very close attention to the units which are mentioned. Okay, so final answer should be in terms of the SI units, okay, not in terms of the CGS, where you have centimeter, gram, and ml units indicated as in the question, but in terms of SI units. Did you get the answer?
Hello.
So the first part where we calculate impeller Reynolds number, you have n d square rho by mu. So you have speed in per minute, so you calculated it in per second, into d square, which is your 60 centimeter. So 60 centimeter, and then you have your density given in terms of 1.45 gram per ml, and you have your viscosity given as 10 centipoise, which is equal to 0.1 poise, right? So this is your equation to calculate your impeller's Reynolds number. If you want to find it in terms of PSI units, then zero point zero 0.01. Which comes out to be 78,300. Yes. Right. So your impeller Reynolds number is 78,300. And then from this, we obviously know that in that case, your power number is going to be constant. That is C dash, as we had seen in the equation. And for this configuration, your C dash was given as 1.05. And using the same, you have 1.05 into 1450 into 0.6 to the power 5 into n cube, which is your 1.5 to the power 3. Right. So I hope after solving this, you'll get the final answer. I think, Shivam, you mentioned as 399 watt, right? Let me just see what we have. Yes, so the answer is 399.5, right? Which is nearly same as what you mentioned, Shivam, around 399 watt. Okay. But then in the exam, there is a good chance that the question of how it would be asked is you are given certain conditions about the tank and everything, and then they'll just mention that from the existing speed, now the speed has been changed to like twice of the original value, or the diameter has been changed from this to this. Then how is it going to affect your power consumption, right? So that is how you have to make use of these two equations and then use the appropriate one to get to your correct answer. Okay. I hope this was clear. Then moving from this, we come to our last topic in mechanical operation, which is the mixers. But in this mixers, we will be talking about those equipments which are used for viscous materials or a plastic or the materials with a plastic nature or something which is a nearly kind of a solid phase that you're dealing with. Okay. So for these mixers which are used for viscous or plastic like materials. Okay. So because they have to deal with these kind of materials, they are very rugged in nature. I mean, they are very uh, heavily built in nature so that they can generate enough force so that these kind of materials can get mixed on a large scale. And because of this, their power consumption also comes out to be very high, right? So these are rugged in nature and also have high power consumption. And among the most commonly ones that are used in industry, they are double arm kneaders, then you have Banbury mixers, and you have Mueller's, and another is ribbon blenders. Okay, there is another type of mixer which is used, although it is not the one which is used for a very highly viscous material, but still those are your tumblers. Okay, so these are ones which are used for like very definite particle sized kind of solids, but not for handling materials which are very plastic like or very heavily viscous in nature. Okay, so in case of mixers, what I would like to do is I will just show you a couple of clips for each of them to give you a better understanding, because from the figures that I will draw, it will not be that much clear. So
Hello, sir. Hello. Hello, hello. Hello, sir. Hello, sir. Am I audible? Hello, sir. Am I audible?
Okay. Sorry, I forgot to turn on the mic. Okay. I don't know where did I stop. Okay. So again, as what I was saying was, as you had seen in the video, uh, the double arm kneader mixer, you can send in the feed through the open top, and then when it gets mixed, when it gets mixed, and when you think that you have provided sufficient amount of time, then you can just you can just tilt this trough so as to get your material out, clean the blades, and then again start feeding for your next batch. So that is how your double arm kneader mixer works. Okay. And the another thing is the modifications which are generally employed in or which are possible to have in this kind of mixer is to use different kinds of blade. Okay. So what we had seen was called as the Sigma blade, whereas the one what we have, I mean the other provisions what we have, they are known as dispersion dispersion blade, and the next one is your double Neben blade. And the first one, what we had seen and the most commonly used, is your sigma blade. Okay. So this dispersion blade is mostly used in the rubber industries or the rubbery masses, whereas your double Neben blade is used for your heavy plastic materials. Okay. And the sigma blade is used to clean and mix very sticky materials, right? So any plastic-like material which is being operated at a, let's say, slightly elevated temperature, in that case, you can use your sigma blade, whereas for more rubber-like material, it is better to use the dispersion blade. So I'll just try to give you a slight idea of how these blades look like. Okay, so your sigma blade was something like this. This was your sigma blade. Again, in the two-dimensional figure, it might not be very clear. So maybe you can refer to the images online. Then you have your dispersion blade, which looks something like these. And then you have your double Neben blade, which is kind of a double trough, or double elevation here. Right. So these portions, what you see here, these are the ones which hold the material together, and then they kind of push it onto the adjacent blade, and then that is how you do the mixing. Right. So because these are very heavy plastic materials, so these double trough or the deformed portion of these blades are the ones which are able to hold that material and then give some amount of time, and then it is being pushed onto the other blade so as to mix it properly. Okay, so this one was your sigma blade, this one was your dispersion, and this was your double Neden. Okay. Then the next mixing equipment is your ribbon blenders. So in ribbon blenders, it's slightly more easy. You have two helical ribbons. Moving in the opposite direction. One of them moves at a slightly slower speed than as compared to the other. So these contracting ribbons are mounted on the same shaft, and one of the ribbons will move the solids slowly in one direction, while the other one will move the solids quickly in the other direction. And because of this counteracting motions of these two ribbons, the solids or the mixture of the solids, they tend to get mixed with each other. Okay, so these ribbons may be operated on again on a continuous or on a batch basis, and the most common application or the most common mode of operation is usually the continuous one, where the turbulence which would get generated as and when when the feed is being sent from one end, uh, the turbulence would get generated, and this counteracting nature would then push the feed in one direction and to the other, and then because of that, the generated turbulence would cause an efficient mixing between the materials present in the mixture. Okay. So these kind of mixer, which is your ribbon blenders, they are very easy for handling thin pastes or the dry powders that do not flow easily. So then using these, it would be very much easy to uh, have a good mix of them, but also it cannot handle a very thick material like how it was in case of double arm kneaders, because in that case the movement which your material has to undergo is very less as compared to the one what it has to go in ribbon blenders, right? Because in ribbon blenders it has to traverse through a long path until the point where where it goes out from the mixer. Whereas in double arm kneaders it was very simple on a batch mode, so you can take it out after switching it off. But here in this case, if the materials used are very thick or very viscous, then it would just clog the operation, or it might just not be or I mean the what do you call, the helical ribbons would not be in a condition to move forward, and it might just jam your equipment. That's why your ribbon blenders are supposed to be used for handling very thin paste and dry powders, right? So next, what we have is a Banbury mixer. So it is again a heavy duty mixer with two blades rotating in the cylindrical sheet. But I think again it would be better if I show you it's working than just giving you two-dimensional representation. So let me just Okay, just 1 minute. The video what I had saved, I'm not able to see that, but okay. In the meanwhile, I'll just give you an idea of how it actually looks like. It is very much similar to that of the double arm kneader, but there is a slight difference, and I'll try to show you until I find
Like
that
your
clip.
friends.
So what usually happens is this is the enclosure. And then just like you how you had two different blades which were moving in the double arm kneader, here you have a different kind of blades which are pear shaped like the fruit. Right, so this one is moving in this direction, and then you have a similar kind of a blade in the other side which is moving in the opposite direction. So again, you've put in the feed here, and here there is a discharge door which when the operation is done, you can just slide it out and then take your material out from it. Okay, so as you see here, this is what your blades are here. Unlike double arm kneader, you don't have the different variations, but you have a very fixed shape of the blades which are used. So something like this here, and then from the because I mean the way it is attached to the shaft here, it will keep on moving in this direction, and then again the motions of these two blades, they might not be in sync with each other, but the one thing which is common is that one thing which it is common with the double arm kneader is that again it moves in the direction opposite to, both of them, they move in the direction opposite to that of each other. Okay, and this particular mixer is also used to handle the plastic, the very heavy and the viscous plastics, as well as in the rubber industry. So because of that, based on the nature of material that it is handling, the machine operates at a very slow speed of mixing, which is somewhere around 40 RPM or even lower than that. Okay, and then during this mixing, it is also possible to operate it at slightly elevated temperatures. And then if in the case during the mixing, if some of the heat is getting generated, you can use the cooling water on the walls of this mixing chamber, and then take that water out, and then through the sliding discharge, and then and you can then continue to keep on having the mixing taking place until the point where it is on a satisfactory level as per the operator. Okay, so this is your Banbury mixer, and then after this we have Mueller mixers. And Mueller mixer, what happens is, so here you have this circular area, and from this you have two outer wheels. something like this on the opposite ends. So these are the wheels here, and then you have two plowing arms. Like this. Okay, and these wheels are, or this entire arrangement, it moves in this direction. So these are called as plows. This is your outer plow. This is your inner plow. These are your wheels. Oops. Okay. So here, what you have is your solid material fed into this particular vessel. So its operation is very much similar to that as that of a mortar and pestle, where you feed in the solid from the top, you let it reach to a certain height within this vessel. So like if this is your vessel, so maybe you feed in the material until it reaches certain height, so that the wheels are able to cover at least I mean most part of that solid. So uh, this is the central shaft. When it is driven, it causes these wheels to roll in a circular manner over the layer of solid which is fed in, and then these wheels are basically kind of uh, acting as the crushing and the grinding part of this mixer, where when you want to have the final mixer, or let's say the feed what you have all the components present, but you need to have them of the uniform size as well as the composition. So these wheels are the ones which make sure that your final mixture is of uniform size, and these plow, they are the ones which initiate the mixing, and because of the direction in which they move, so these plows then direct the solids towards these wheels, so that after one point all the solids which are present, they become of the uniform size and then also get mixed to the same extent. So these plow have two purpose. One is to initiate the mixing as well as direct the flow of solids towards the wheel, so as to have a uniform size of the solids which it is handling. Is this clear? So those I mean these are used in case of the solid materials which are of relatively large sizes, and also uh, some heavy pastes which have to be mixed and also have to be beaten down, so that they have a slightly smooth flow of smooth flow of movement, and then because of that it will be beneficial to have a more uniform composition of the material throughout your feed mixture. Okay, so for this also I'll try to give you an idea from So this is something like this. So you can see these wheels are moving, and the clouds which are you see, these are the ones which are directing the flow of solids into the wheels for crushing them and obtaining fine grains or very narrow pieces that solid sizes. Right. So I hope this video was able to give you a clear indication of what the Mueller mixers are. I mean, their overall operation is slightly different because they carry out basically two different types of operation at once. That is grinding and the mixing. But they do have very significant applications in the industry because of their dual functionality. Okay, and then the last one is the tumbler. And again, this is something which you must have seen very often whenever there is a kind of, I mean, the roadside construction is happening. So you, especially the places where the cement is being used quite a lot. So in those cases, you must have seen this tumbler. So of which the most common is the double cone tumbler. So what you have is this, and this tumbler here. This is attached to a support. And then this tumbler moves, or it rotates on this axis, which is perpendicular to the line joining the point of the cones. And you have both the ends of the cones these are close, and then the solids, and as and when these this particular vessel, as it moves or as it rotates, the solids are tumbled down. So in this case, there are chances that if the solids are not those I mean that hard nature solids, then there is possibility that there might be some kind of attrition which is taking place, which might again result in the reduction in the size of solids, and also at the same time it would lead to the mixing of that material within, right? So this double cone, this is what we call it as the double cone mixer. Okay, so as I mentioned, it is mounted such that it can be rotated on the axis perpendicular to the line joining the point of cones, this. And I mean, even though like let's say you are given the total capacity of, let's say, around 100 liters of it, so you do not try to fill it to its maximum capacity or somewhere even like 70-80%, but the maximum that you would want to fill, so that you provide sufficient amount of area or sufficient amount of contact between the different materials within the feed. So for that purpose, you keep it to somewhere 50 to 60% of its capacity. I mean, you try to fill in the material, which is up to 50 to 60% of its total capacity. Okay. So again, just like how we had Mueller mixer having two different functions being carried out at the same time, same is the principle for the tumblers, where you have uh, size reduction as well as the mixing of material taking place at the same time. Is this clear, Shivam? Okay. So with this, we have finished the theory portion of mechanical operations. And I remember last week I was in the last class I was supposed to send some numericals, but I forgot. I thought that I've already shared it, but I'll make sure that I'll send it today. So we have completed the theory portions, and based on whatever we have discussed, there are only certain types of numericals uh, which can be asked, and based on that, I will share some questions today without fail. And after this, we will move towards our next subject, which is chemical technology. Okay. Yeah. So just give me 2 minutes. I'll be back online. Okay. So our next subject is chemical technology. So one problem with this subject is that this involves very less understanding of the concepts, but more of memorizing the things. So in this, it's going to be more like, giving out the facts and then just understanding them a bit and then remembering them is the only option that we have in this subject. Okay. But still, we'll try to reason out the things which are mentioned for the different processes and in the different industries. right? So let's start with that. Right. So in chemical technology, we will be dealing with the four different types of industries. Okay. So one is going to be polymer industry. Second is going to be petroleum industry, right? And within that petroleum industry, I mean, one is the point until which you obtain your crude oil, and then from that, from there, you have your petrochemical industry. So this is petroleum and refining, and then you have then petrochemical industry, and then four is you have your product based, where you are mainly focusing on your final products, like let's say paper and pulp, soap and detergent, oil and fat industries, fertilizer industry, and so on. Okay. So first, talking about the polymer industry. So we must have, I mean, it is very commonly known what polymers are, right? So the polymers are like large chain molecules which have a very high molecular weight, and they are mostly made up of multiple units of one single molecule or one single type of molecule, which is repeated several times within that structure, right? So this repeating unit or that repeating molecule is known as the monomer, and the process is known as the polymerization, right? So the most common example is your polyethylene. So you have one molecule of ethylene. When it is made to undergo polymerization reaction with n number of units of it, what you obtain is a polymer, which is your polyethylene, right? And this polymerization reaction, there are different ways of doing those reactions. One, like such as your addition polymerization, and then condensation polymerization, etc. Right. So this process polymerization can be carried out like the one, I mean, using several types of reactions, one of them being the addition polymerization. Right. So in addition polymerization, the reaction occurs by the formation of a long chain where each monomer is repeated a number of times and no elimination of any small molecule takes place. So just like in case of polyethylene, whatever the molecules of ethylene that you're taking place at first, they are just getting reacted with each other to form a long chain. And then that gives you the final polymer. And you do not have any other byproduct or any uh, other component getting formed during the reaction, right? You do not have any separation out of water or carbon monoxide or any other kind of molecule. It's just simple addition giving you the final product, right? And this kind of addition polymerization reaction is slightly common when you have your initial feed material, which is an olefin or a material which consists of a double bond or a triple bond. So these kind of feedstocks, they undergo addition polymerization reaction more commonly, right? Then the next one, what you have is your condensation polymerization. Here as well, you have two or more. So like in case of addition polymerization reaction, you had only one unit getting added up several times to give you the final product, right? Whereas in condensation polymerization reaction, you have two or more than two monomers which combine together to form a new compound, which is having a functional group different than the initial one, but it also accompanies with, it is also accompanied with the elimination of small molecules, like as I mentioned, water, hydrogen, NH3, CO2, anything like that, right? So that is your condensation polymerization reaction. So here, let's say you have an example of a carboxylic acid. So COOH giving, COOH, CH2,4, and COOH plus an aniline where you have NH2, CH2,6, NH2, giving you a polyamide, right? So here you had an acid, here you had an aniline, but the resulting product is an amide with functional group HNCO, CH2,4. Okay, let me just write it in a better way. So you have HNCO, CH2,4, HNCO, CH2,6, CO, and so on. So you have like n repeating units of both of them. So here you have n of this, you have n of this, plus n of H2O, right? So you have two monomers having two different functional groups reacting together to give you a polymer which has functional group of amide, but it also accompanies with the removal of smaller molecules such as that of water, right? So this is an example of condensation polymerization reaction. Is this clear, the difference between the two of them? Right?
Yes, sir. Clear.
So now there are different techniques to carry out addition polymerization reaction. Which includes bulk polymerization, solution polymerization, and emulsion polymerization.
Polymerization.
So bulk polymerization consists of a reactor with certain monomer units. You have an initiator, a chain transferring agent, and a chain terminating agent. Okay. And this mode of polymerization is usually employed when you have to obtain a very purest form of polymer, when it is a mixture of polymer that you have, or when the purity of it does not matter much, but the cost is something which is important, then you can opt for the other techniques. But in terms of purity, this is the one which gives a more better suited approach, right? So you have a pure liquid or the gaseous form, like in case of ethylene and propylene, you have the gaseous monomer. These monomers are then subjected to the polymerization condition. The reactions are more or less exothermic in nature, and then the biggest concern what you have during the reaction is the heat removal. Okay, so for that, it is very important that you have a cooling system provided along with the reactor or during your entire process, so that it uh, so that the polymerization reaction does not get prolonged to such an extent, then after which it becomes uncontrollable, and then you reach a condition called as thermal runaway, where it becomes nearly impossible to stop the reaction, and the amount of heat which is generated during the polymerization reaction, it leads to a big hazard. Okay, because of the enormous amount of heat which is generated during the process, right? So that is what happens in the bulk polymerization reaction, and it becomes very important that to maintain the purity and to avoid having any interference of any other component into your final composition of polymer, it is needed that the solution that you take at the initial, it consists only of the bulk number of monomer units, and it is provided appropriately to counter the excess amount of heat which is generated during the polymerization reaction, because compared to the other ones, which are solution and emulsion polymerization reaction, this is slightly more difficult to handle in case if there are any possible hazards associated with the process. Right. Then you have solution polymerization, where an inert solvent is added to the reacting mixture in the vessel, and this solvent enhances the heat capacity and therefore facilitates the heat transfer, because of which one of the drawbacks of the polymerization was that in that case it becomes much more difficult to have remove the heat, or in case when there is a polymerization reaction taking place, it's possible that again there would be formation of some localized heat spots where at certain points in the vessel you have so much amount of heat which is accumulated there, but at the other sections of the vessel there is no heat which has reached there, right? So in that case, even though you provide the mode of cooling down the vessel, it will not be able to remove the heat as efficiently as it should have been, right? So in the solution polymerization, that is one of the advantages. So during the process, some amount of the solvent can be refluxed to remove the heat from the reaction vessel, and because of the presence of a solvent, the solution polymerization technique reduces the reaction rate and the molecular weight of the compound, right? Because then you have a material which is interfering with your material, and because of that, the concentration of your monomer units would get decreased down, and as the concentration gets reduced, your reaction rate is going to get reduced down, and hence you are not allowing much of those monomer units to come in contact with each other to get further added down to make a polymer, and hence you will have the overall molecular weight on the lower side as compared to what you can obtain in the bulk polymerization, right? So the third one is your emulsion polymerization. So in order to control an enormous amount of heat released during the bulk polymerization, the suspension polymerization again has a similar approach as that used in solution polymerization. So the reaction mass is dispersed or suspended as minute droplets of a very small size, somewhere like around less than 1 mm. And each of these tiny droplets then acts as a small reactor in itself, and the heat transfer from the droplets then occurs to uh, the liquid medium which is used to obtain this emulsion, and then this liquid medium which is used to obtain as the emulsion acts as the heat sink, which takes up the heat which is generated from these tiny molecules which undergo the polymerization reactions, right? And for this kind of polymerization technique, agitators are used along with the suspension or the emulsifying agents in the aqueous phase. so as to maintain a very specific droplet size and the suspension, because the more control what you have over the droplet size, more narrow will be the distribution for the polymers that is obtained in the final product mixture, right? And once you are able to maintain that specific droplet size, the polymer which will be formed will the polymer which will be formed from these tiny droplets, or these kind of droplet reactors, they will have a very uniform size as well as characteristics as compared to the overall bulk properties of the polymer that you have obtained at the end, right? So these are the different techniques to carry out the addition polymerization reactions. And then based on that, and based on the monomer units that have been used during the reactions, you have different types of polymers. So the classification of polymer is based on, I mean, there is not only one way, but there are a couple of different ways. So first one is based on the arrangement of monomers. So first one is a homopolymer, where you have one unit repeated one after each other. So like, and if M is your monomer, then these units of M attached one after the other, that is your homopolymer, right? Then you have a copolymer, when you have two monomeric units added in the random fashion, something like that. So this is your copolymer, right? Then you have your block polymer, where you have a very specific arrangement of the monomeric units in a very definite fashion. But these block polymers are arranged in a linear manner. So something like this. So basically you have a repeated unit of two monomers attached to each other in certain specific amounts. And when these repeating units are added further, it gives you a block polymer. Then after this, you have graph polymer, where you have branches along the main structure of your polymer which is formed. Okay, so these are this is the classification of polymer based on the arrangement of the monomeric units. And then you have, based on the properties, they are classified as so based on properties, they are classified as thermoplastic, thermosetting plastic, and you have elastomers, and you have fiber. Okay, so thermoplastics are the ones where from the application of heat and pressure, the polymers, the polymer then becomes soft and can be molded into any kind of shape, and this can be used again and again. So in such, the plastics or the polymers having such properties, they are called as the thermoplastics. Okay, so the thermoplastics are the ones which have which are linear in structure or have very small degree of branching associated with them. Okay, then you have thermosetting plastics, which consist of a network of long chain molecules, which are like the cross-linked molecules, cross-linked polymer. Cross-linked polymers are the ones which have a three-dimensional structure, and over these polymers, when you apply certain amount of heat or some amount of pressure is applied to it, they become hard and then they cannot be molded again or cannot be used again and again. Okay, so that is your thermosetting plastics or thermosetting polymer. Then you have elastomers, and the elastomers are the resistant solid which have considerable flexibility and are composed of polymer which have how do I mention that? Have you heard of the term called glass transition temperature? No? Okay, so glass transition temperature is basically the temperature at which any material changes its state from where it is more like a more like glassy nature to a rubber kind of behavior, or the rubbery nature of it. So that temperature is what we call as the glass transition temperature. And glassy state, the rubbery state, we know that it is the point where the material is flexible and elastic. But the glassy state is the one where the material is hard and brittle. Okay. So elastomers are the ones which have considerable flexibility, and these are composed of polymers which have glass transition temperature below room temperature. Okay, so anything above, at an above room temperature, all of these materials are bound to act as a rubber kind of a material, right? So those are the ones which are called as elastomers. And then the fourth one is your fiber, which are nothing but solids which can be formed or which can be made into a thread-like structure or thread-like appearance and have a very high tensile strength, right? So to give you an idea of what kind of polymers are involved. So thermoplastics, for example, polyethylene, that is commonly indicated as PE, polypropylene, that is PP, PS is your polystyrene, PVC, which is polyvinyl chloride. These are all thermoplastics. Then you have thermosetting polymer, which are more like epoxy resins. Then you have phenol formaldehyde, melamine formaldehyde, etc. Then among elastomers, you have SBR, which is your styrene butadiene rubber. Then you have your butyl rubber. Then nitrile. This is something which is used to make your laboratory-based gloves. So nitrile gloves. So those are the ones which are which come under elastomers. And then you have fiber, which includes polyamides, polyesters, which we know is used in the textile industry. And then you have like cellulosic fiber derived from the biomass or bio-based feedstocks, and acrylic fibers. Okay. So these are the ways in which we have different classifications of polymers. And in the next class, we will look further into some commercially important polymers, which is